approximate solutions to AX equals B. So we know how to get this part now. We can start off by Q1 is a normalized B. We can get subsequent Q's using the Gram-Schmidt process from a previous board. Now we just need to know how to get this. So what we do is our goal in choosing YK is to minimize the norm of our residual, B minus A xk. So let's go ahead and take a look at this and see how we can minimize it. Okay. Now, if I keep in mind that B is R0, and then xk is qk times yk. So yks are unknown. Everything else in here is known. But now I can do some simplifying in here. So R0 is the 2 norm of B times Q1. And then AQK becomes QK plus 1 HK tilde. And we still have a YK. Now, Q1, that would be QK E1, because Q1 is the first column of capital QK. Now, there should be a tilde here. Now what I can do, this is a vector 2 norm. I can multiply this expression on the inside by any orthogonal matrix, and that preserves the 2 norm. So, so what I get is, I can basically cancel, it has the effect of canceling out these q's. In fact, I could do this. So what I get is beta naught E1, where for convenience, beta naught is just the 2 norm of B, minus HK tilde YK. Right. Now, so what I'd like to do, everything here is known except YK. So I want to choose YK to make this as small as possible. What I'd love to do is make it 0. But how come I can't do that? And if this were a traditional AX equals B problem, I could go ahead and solve the system and be done with it. But what's the problem here? What is it about the matrix that prevents me from solving this exactly? Once, going twice. It's not square. HK is square. HK tilde has an extra row at the bottom. So, so this system in general does not have an exact solution. We'd love that because then we can solve AXB without really doing much iteration at all. Yeah, HK tilde is a K plus 1 by K matrix. So this is an example of what I talked about last week. It is a full rank least squares problem. Because all the PLL subspace vectors we're generating are linearly independent. that means that HK tilde as well is going to have linearly independent columns. So we can solve this problem using methods I described last week. So performing a QR factorization on HK tilde, but this is a small matrix. So the expense of that should not be great. Or using the normal equation, something of that nature. Also, the fact that HK tilde is upper Hessenberg, that sparsity makes it easier to solve this problem. So in fact, to compute QR factorization of a Hessenberg matrix, you only have to eliminate those subdiagonal entries. So the work involved is order k squared, whereas it would be k cubed for QR factorization of a general matrix. So, so we do gain something quite substantial by reducing, by obtaining this Hessenberg form for the least squares problem. Okay, so what this does is it at least makes the residual as small as possible. So now what I can do finally is describe the overall algorithm that solves AX equals B for a general invertible matrix A using this approach of generating this orthonormal basis from a pre-law subspace and then solving a small least squares problem based on that. Okay. So the method I've just described at length, I'll summarize here, is the generalized minimum residual method, also known as GMRes. So first some initialization on H10. So because of the zero index, it's not really an entry of capital H. Right, so first I'll set R0 equal B, and then H10 is the normal R0. And I'll set J equals 0 to start our iteration count. So as long as our subdiagonal entries, well, they're always going to be non-negative because they're norms of vectors. So as long as they're positive, we'll keep the iteration going. So Qj plus 1 is Rj over Hj plus 1j. So this is valid even when j is 0 because of these initializations up here. Okay, now I'll bump up the iteration count. Okay, so now I have Rj as my okay, I'll fix that later. Hij is Qi transpose Rj. I have Vj in the notes, so that's another thing I need to fix. And then I update Rj. Hij Qi. So this right here is the Graham-Schmidt step that's being performed. And then I go ahead and compute my subdiagonal entry of H, which is the norm of a vector that's left after I subtract off all these terms. And then my last step is I compute my iterate. So xj is qj, yj, where yj is a solution of my least squares problem that I described on the previous board. Alright, so we're solving this full rank least squares problem. That's for J column matrix with each iteration. Okay, so this is a GMRes method. I should mention that all this work that's being done here to produce these Qs, that is a very important algorithm called Arnoldi iteration. So really you can think of Lanczos iteration that gave rise to conjugate gradient as a special case of Arnoldi iteration. Lanczos iteration applies when matrix A is symmetric. So Arnoldi and Lanczos iteration both are useful for finding out information about the extremal eigenvalues, largest or smallest of A. But they're also very useful for solving system linear equations like AX equals B, or computing matrix functions and so on. Okay. Now, one big drawback of GMRes that is not relevant for conjugate gradient is the following. So this is a least squares problem, LS least squares with a J plus 1 times by J matrix, this HJ tilde. So that means each iteration is going to require more work than the last. Not only because of this growing least squares problem, but also because of the Gram-Schmidt, because we're subtracting off more and more terms of each iteration. So each iteration requires just a single matrix vector product, but there's more dot products. So the expense is growing from iteration to iteration. Unlike conjugate gradient. In conjugate gradient, each residual depends only on the previous two. So each iteration is about basically the same amount of work. So how do we get around this? What we do is in GMRes, we restart the iteration. So the idea is we go ahead and we compute iterates up to a certain point. When this problem starts to get too large for our taste, we stop the iteration, and now this serves as the initial guess that feeds into the next iteration. So so that what we could do is, after we compute xj, we compute a residual from that, and that becomes the R0 to start this all over again. So restarting iteration sets us back to a tiny least squares problem, a tiny Krylov subspace basis, and we just go from there. So, for instance, there's a GMRes function in MATLAB. So one of the parameters that you need to specify for using GMRes in MATLAB is how often do you want to restart? What is the largest size of a least squares problem that you can tolerate? So this is something that's not a non-issue with conjugate gradient. Okay. The conjugate gradient is for the symmetric positive definite case. Now, the last thing I'll talk about is, what about an intermediate scenario? Suppose A is still not positive definite, but is at least symmetric.